Or that better?
Give me a wing. Okay.
Yeah, I'm going to do 2 and then 1.
All right, I'm Jontof-Hutter. I'm a research associate at Penn State University. I'm going to be talking about characterizing planetary masses, radii, and orbital eccentricities using transit timing variations. I'd like to thank my collaborators Eric Ford, Jason Rowe, Jack Glissauer, and Dan Fabrici. So you've all seen this. This is Kepler's period radius distribution. And here is Earth's radius, here is Neptune size. And it turns out that planets between Earth and Neptune in size are really, really common. And we don't have any examples like that in the solar system, but it's a very interesting sort of size range of planets to study because this is the transition from rocky planets to planets that retain deep atmospheres. And so for most of these planets, we're never going to get their masses, we're never going to be able to characterize them. And here's a sample of the ones that we have been able to characterize. In green, I've got the published radial velocity masses, and they sort of range from the closest to the star out to the region here. In TTVs, we're measuring planetary masses from about 5 to 200 days. So it complements the RV sample really nicely. There is some overlap as well. There are some planets where there's both RV and TTV data, which is fantastic. But we're managing to sort of push the detection of low-mass planets and characterize them out towards the habitable zone with transit timing variations. So transit timing variations, we're detecting the perturbations between planets that can cause their orbital periods to change very slightly. And because we can measure their transits to the transit times to high precision. So let me give an example. This is Kepler 79. There are 4 planets near a 1, 2, 4, 6 resonance chain. They're not in resonance, they're near resonance. And so their perturbations are coherent for tens to maybe 100 orbits, and you get a TTV signal. You get changes in the orbital period that you can detect. So we want to characterize these. And here are the TTVs for the innermost planet, B, C, D, and E. And we're going to fit a dynamical model to the system. The first assumption is that we're going to assume the orbits are coplanar, and that's a really good assumption because we know Kepler's multi-planet systems, the compact multis, have got a low inclination dispersion. We also know that inclinations are a second-order effect in TTVs, so this is a pretty strong assumption. We're also assuming that there are no non-transiting perturbers that cause the TTVs that we observe. So there could be a 5th planet in the system, but as long as it's not near resonance with one of these planets, it's not going to confuse our model and give us bad results. You could have a planet interior to, you can't have a planet between B and E, the system will go unstable anyway. But interior to B or exterior to E, we are unlikely to be stung by a planet there because the periodicities that we see in the TTVs match up with exactly what we'd expect, given how close the observed planets are to resonance. So we'd be very, very unlucky to be stung by a non-transiting perturber. So the parameters we're going to solve for include planetary mass, orbital period, orbital phase, eccentricity, and the argument of periastron. So here is our best fit TTV model to the system. The innermost planet, B, has got a very sinusoidal signal, so there's not much more information in the TTVs other than just the amplitude of that sine wave. Whereas you can see the other planets have got more complex signals, more information-rich TTVs, which allows you to get much more precise constraints on the planetary parameters. So here are the results for Kepler 79 from TTV analysis. Firstly, we get dynamical masses. We get the planet masses relative to the host star. And obviously, if you don't know the mass of the host star, you can't actually get the actual mass of the planet. So here I've given the planet MP over M star multiplied by M sun over M Earth. So you can get approximate Earth masses. And once you know M star, you can just multiply it in. So we get dynamical masses. We also get very good constraints on eccentricity. These are very low eccentricities, but we're still getting detections of the eccentricity, which is not something you can do in RV for eccentricities less than about 0.1. And these are very useful because they can give us constraints in stellar density and hence the stellar radius. So it's not just the mass that we need for the star, it's also the radius of the star, because the transit depth only gives you the size of the planet relative to the size of the star, and you need good constraints on the stellar radius too. But So this equation is saying that the stellar radius to the size of the, compared to the size of the orbit of the planet, depends on a whole bunch of stuff from the transit light curve, the transit depth, the transit duration, the ingress duration, and the orbital period, multiplied by some function of eccentricity. And normally with transiting exoplanets, you have no choice but to assume the eccentricity is probably around 0. You let this function equal 1. But you can see that even eccentricities as low as 2% would give you a 2% error in R star over A, and a 6% error in the stellar density. So with our tight constraints on orbital eccentricity from our dynamical models, we can get better constraints on the stellar parameters. So we've constrained the stellar parameters for Kepler 79. It's slightly more massive and larger and hotter than the Sun. I'd like to impress upon you the uncertainties that we have on the stellar radius. That's just 2%, which compares very favorably with other hosts of low-mass exoplanets on the mass radius diagram. And so I have a running rank list here. Stellar radius uncertainties for sub-Neptune mass hosts on the mass radius diagram. If you can directly measure the size of the star with interferometry, obviously that's the best thing you can do. In the Kepler field, astroseismology is a gold standard. There are a handful of stars where we have useful astroseismology detections, and uncertainty is down to 1 to 2%. But short of that, with our dynamical constraints on the eccentricities with TTVs, alongside light curve analysis and high-resolution spectra, we've got uncertainties on Kepler 11 and Kepler 79 down to just 2%. So we've characterized the star. We're ready to characterize the planets. They're all super-Earth and sub-Neptune mass planets. They've got a range of sizes and a huge range of densities. The standout line here is Kepler 79D at less than 0.1 grams per cubic centimeter. It's super-Earth in mass, but its density is comparable to the air in this room. So it is something of an anomaly. Here it is on the mass radius diagram. All these planets are, so these are compared to models of iron, silicate rock, and ice. And so all the planets above the ice line, the ice curve, must have deep atmospheres. And all these planets have deep atmospheres here. This one, Kepler 79D, at 6 Earth masses and 7 Earth radii, it's not an outlier or a mistake. It's a very robust mass determination, and I'll give you 2 reasons. The first one is that the system is compact enough that it's almost unstable. If we use the 1 sigma upper limits on our masses, the system would be unstable. And secondly, Kepler 79D is interacting with 2 of its neighbors, Kepler 79c and Kepler 79e, and both of the TTVs from both of those planets give constraints that agree and say that this planet is just 6 Earth masses. So since we published this early last year, it's been joined by others. In this diagram, I color code the masses and radii by the method. So RP is in gray here, and TTV is in orange and red. Orange are all the published TTV results, and red are the ones that I've worked on. And so you can see differences, like RV and TTV are clearly looking at different sort of populations of planets. But anyway, we've identified here a small sample. It's not the most common type of exoplanet, but there's a small sample of extremely low density, low mass, super Earth mass planets. And these ones are just not detected in RV. And so you might ask why. Well, if you had, this is showing planetary mass and orbital period. Well, these ones are all up here. If you wanted to detect a 6 Earth mass planet with RV, it would have to be orbiting in 2 or 3 days or less. And so those planets would just be too hot to retain their deep atmospheres. So there is a detection bias in RV against finding these extreme low density objects. So both techniques have their biases, and I'll just summarize them quickly. RV, high mass planets at a given size is what you're going to detect. And the low mass planets must have really short orbital periods. And this means that the lowest mass ones, the hot super Earths that have been characterized by RV, are too hot to have atmospheres anyway. And also, this might be a population level bias. The coolest stars are the best targets for Doppler observations. It may be different by spectral type. So for TTV, we also have biases in TTV. For a given mass, we characterize systems with larger planets. There is a bias towards lower densities, because the larger planets have got the deeper transits, the more well-characterized transit light curves. And so those are the best systems to do a TTV analysis on. So we have this bias towards lower densities. There might also be a population bias. We don't really know whether these sorts of planets are more common in compact multi-planet systems because those are the best ones for TTV analysis. So there I'll conclude. Super-Earth mass planets, that range from 5 to 200 days in orbital period, have an enormous range in bulk density. They could be, they're super-Earth by mass, but they could be super-Earth in size or up to Saturn in size. And my second conclusion is that with precise eccentricity constraints that we get from TTV analysis, eccentricity constraints that are below 0.1 are awesome in their own right, but they also help us improve stellar parameters and get us better planetary radii and therefore meaningful bulk densities for planets.
Have you given any thought to how these low density, low mass planets form? Because normally you would expect those are too small to have such a large atmosphere.
That's an extremely interesting question. And so there's, I mean, the textbook says that with core accretion, you need sort of 10 Earth masses before you can start accreting a deep envelope, and that can be thrown out the window. So any idea is a good idea at this stage. You would be. So you're the moderator.
Hi, so your ultra low density super Earth, is there any preference for very short orbits close to their star? Do they disproportionately?
No, TTVs, if anything, favor longer orbital periods because you get more information if you can have more orbits per TTV signal. You get TTVs improve much more with orbital periods. So the longer orbital period ones are better to characterize with TTV. That's just like an observational thing. Theoretically, apart from mass loss, I can't think of anything else that would distinguish, that would favor these planets being found by TTVs over RVs. Yeah.
You mentioned theory, but the hot readers have a well-known for several hypothesized methods of inflating them. Some of them are much more powerful if they're close to this whole star, for example, like omega dissipation. So maybe something similar to do with super like
I couldn't hear all the question. I'm sorry.
What I meant was for the hot Jupiters, which also have extremely low densities, you have hypothesized omega dissipation, for example, which would work strongly if the planets are close to their whole star. So I'm wondering if that would be an explanation.
I haven't put any thought into that.
For any pairs of the planets in the system, are any of the secular angles vibrating at all? Because you said they weren't in resonance, but is there an axial lock in any planet pairs?
Not in this system. In some systems, you do get with TTVs an eccentricity degeneracy. And you can have sort of eccentric orbits that are stable because they're axially locked, like you say. But you can't tell whether they must be axially locked because you can't tell if they must have the high eccentricities or not. So you can say that sort of a certain fraction of your solutions have axially locked high eccentricities, and a certain fraction are just low eccentricity, and it doesn't matter. But you can't say either way for the systems that I've looked at.
And that doesn't affect the mass?
For the ones that I've looked at, their masses are robust against this eccentricity.
All right, why don't we thank Daniel again?